All right. Hello, everybody. My name is Asad Mirza, and on behalf of AEMB, I'm going to present you guys a workshop on Ansys, specifically the CFD related portion, so the computational fluid dynamics. Yesterday, we had the FEA, or the finite element analysis, which was for structural mechanics. Today is fluid. So, might as well reintroduce myself, same as yesterday. I work in the biomedical engineering department here at FIU under Dr. Shravan Ramaswamy, and I'm currently doing a PhD project regarding TAVR implementation for patients who have calcific valve disease, which involves a lot of finite element analysis, structural mechanics in terms of placing stents in patient geometries and then running fluid models on them using CFD. And this is all done through Ansys, along with some coding in MATLAB as well, but that's the side thing. So that's sort of my bread and butter here. So without further ado, let's get to it. So first off, to do CFD in Ansys, you use what's called Ansys Fluent. It's a CFD software that's capable of modeling flow, turbulence. You can even do heat transfer, because really heat transferring is like a fluid. You can also handle chemical reactions of any kind. And because this is BME oriented, I'm going to throw in a bifurcating artery as the demo we're going to handle today. But the first things first, we have to talk about how Ansys Fluent solves the fluid model under the hood. So for the FEA, it solved the equation of motions, which was in a steady state just force is equal to kx. In this case, it's the Navier-Stokes equations, but it's still force is equal to mass times acceleration, except you have fluid density being like your mass, you have your acceleration, one being your dv/dt term, and one being the effect of the speed and direction of the fluid, the convective term essentially. Then you have all your forces on your fluid. One is the internal pressure gradient. So something's higher, something's lower, there's more force here than there is downstream, pressure gradients. And then you have your external forces. In this example, there's gravity, but if you have like a piston pushing it or something, that would be one of your external forces. And then you have the internal stress forces, which are called the viscous effect. So this is literally fluids as little particles rubbing up against each other and how much they affect the surrounding fluid. And this is captured by what's called mu, which is your viscosity. And if you just sum up all these forces, and you know what your fluid density of your fluid is, then you can figure out what your accelerations are. And if you can figure out what your accelerations are, you can know what the displacement stresses are, shear force effects, and how the fluid's moving through your field. And then you can gain insight on that depending on what it is you're modeling. For us, what we're going to be looking into is this bifurcating artery geometry. And what we're going to have is blood flow going from the inlet to the outlet. So we have this planar surface here, which is going to be our inlet. And we're going to say the velocity is normal to the wall. And then it's going to flow, diverge here at this bifurcation. But if you notice, we have this sort of aneurysm sort of bulge here that's occurring, which is basically a loosening of this wall. So the flow is going to divert here. It's going to go one way for outlet 2. And then one way for outlet 1, and the flow will likely take a longer time to go through here, and it might get trapped in this little pocket area here, which could cause issues in terms of thrombus, in terms of platelet aggregation, but we'll see what happens. And as far as everything along the wall, we'll just say once you get towards the wall, the velocity is going to be 0. This is called the so-called no-slip boundary condition. We're going to use the density of the fluid as 1,060 kilograms per meter cubed, which is a rough estimation. And instead of going for a non-Newtonian fluid model, we're going to keep it very simple. We're going to say the viscosity of the fluid, meaning how difficult it is to flow, is set at a constant 3.3 centipoise, which is good enough for at least demonstration purposes today. So our inlet diameter is about 6.3 millimeters, and outlet 1 is about 4.5, and outlet 2 is about 3. So that's makeup of how our geometry looks like. Any questions before I continue?
Yeah, for the geometry, usually do we make it using splicing software or splicing models? Or like TDT for splicing, yeah, that's what it's called.
So the geometry, you can either make your idealized geometry by actually going into your CAD and say, okay, I want to make a tube that is this much and then draft it and then whatever. But in terms of a patient-specific model, usually what's done is you'll get what are called DICOM images, which are a special type of image native for medical type of files. So like CT images, MRI images and stuff, those come as DICOM files. And what you can do is, let's say it's a CT image. CT image works based off of the intensity or reflection of the tissue it's going through. So some tissue shows up as white, some tissue shows up as less white, and then anything that's empty or blood which will show up as just black because the CT image can't see it. So then you can segment everything that's white in your DICOM image stack, extract that as a sort of a rough STL file, and then go into your CAD model and then turn that STL reconstruction into an actual 3D geometry. And Ansys has tools specifically meant for that using Ansys Baselane. But as far as I know, you can do the same thing in most general CAD softwares nowadays. Yeah.
Sounds good. Thank you.
No problem. All right. So let's go ahead and just jump straight into Ansys. Now, naturally, I've already done this before, so we have all of the results here. But starting from the beginning, what we're going to do is, instead of going for the static structural like we did yesterday, we're going to go up here to Fluid Flow and click Fluent. And that'll give us an equivalent little node setup here where we have to go from geometry to the mesh, to the setup, to the solution, to the results. So let's go ahead and attach our geometry. And it's the same one I showed in the picture. And I have it as a step file. So that's done. Now let's go to our mesh and click Edit. And this is going to start up Ansys meshing. So here we have our nice little geometry. And first things first, I'm going to do my boundary selections. So this is going to be our inlet. So if I click here and make sure you're in the face selection mode, and if you click here, right click, create a name selection, I'm just going to call this my inlet. And then because both of these outlets have the exact same outlet condition in terms of pressure, I'm just going to select both and have them both under a single name selection. So these are going to be my outlet. And now I need to select the entire wall. So if I press Control A, that selects everything. But if I press Control Click now, I can deselect the outlets and deselect the inlet. Right click, create name selection, and this is my wall. And with this out of the way, now I have a name selection that has my inlet, my outlet, and my wall. And by default, Ansys will try to make a mesh for you that it thinks is best. Now, as I said yesterday, what Ansys thinks is best is not really the best. It tries its best, but it's not really good. So the first thing I suggest you change is the element order. Make that quadratic. And by default, Ansys thinks we should use a element size of 3 millimeters, meaning the largest element size that will be allowed on this model is 3 millimeters in length. Meaning, if I were to zoom in here, it will use an element that goes from about here to here as the largest element, and everything will be scope based off that. And it's not going to give the best results, as you'll see. So if I click generate, you'll see it's going through each face, each line, each edge, and trying to make it. And right now we're at 5%. And let's see what it made. So it made a mesh, so that's good. But it's not exactly the best mesh. Specifically, if you notice here, we have these localized areas of really dense mesh that exist for no inexplicable reason. And they exist because of underlying issues with our geometry, actually. So if I turn off the mesh here, this area right here is where 3 different points meet in our actual CAD geometry. And Ansys didn't know how to deal with that, so it just made a mesh really dense there. Similarly, we have another issue right here, where we got a dense part of the mesh here, which is where 3 points meet up. And then as well as over here. And this is an issue because this is not like there's a detail here or a high curvature that leads to this dense mesh. It's really just an underlying CAD issue that was causing this. So now is where we don't trust Ansys and we go based off our own intuition on how to make the model. So what I say first is dump this down to perhaps 1 millimeter in terms of your mesh size. And for sizing, turn off capture curvature. And if you turn off capture curvature, it won't try to capture these strange points of discontinuity here. And while I'm at it, if I go and show you guys what the element quality is, you can see here we have ranging from 0.28 to 0.99. And in the regions of wherever these little singularities are, you get nicer quality, but then it gets worse as you go off from it. So not exactly the best, but now that I've turned off the curvature and we go ahead and generate again, let's see what it gets. So now at least it's a bit more uniform how it looks like. And if I go back to the normal element view, you can see now it's at least uniform in terms of its mesh, but it's a bit coarse, really. And you can tell it's coarse by going under statistics here. It's only 14,000 nodes. And as reference, usually when I do my serious fluid simulations, I go upwards from 500,000 to 1,000,000 plus elements. So in this case, let's first work on these what are called boundary layers. So basically, sometimes, at least in blood flow, we care about what happens when the fluid is really close to the wall. So to capture those effects, we're going to need what are called boundary layers. So we can actually make that by inserting. Yes? Something happened? Nope. So we're going to need what's called a boundary layer, or Ansys calls them inflation layers. So we're going to click this entire geometry, and that's going to be what's going to be scoped to. And for the boundary scoping method, let's switch this to name selection, and let's switch over to our wall. Basically, we want a boundary to exist at our wall. And now if I click generate, you'll see that we do have these boundary layers existing here, but it's a bit coarse in the center now. So what I would suggest is we lower this down to about 0.5 perhaps. Run this again. And this is looking much better. So you can see here, we're capturing what's going on along the wall, as well as what's going along in the interior. Now, one thing of note, though, is we have this bulge region right here that we're really interested in. So why don't we make it so that the geometry in this region is more detailed than everywhere else? And we can do that by doing what's called the sphere of influence. So first things first, let's make a new coordinate system that is centered around this model. So about right here. And what we can do is insert a sizing method, and it's still going to be on this model. And instead of being based off element type, we're going to click sphere of influence. The sphere center will be this coordinate system we just made. And if we do 10 millimeters, let's say, you can see this little bubble form, which is going to be the sphere of wherever the influence is. And let's say within this sphere, I want element sizes to be about 0.25 element size. And actually, if I went for the original, it might be better. So if I went for the original coordinate system, we might get a better result. So if I go 12, almost there, 13, 15. So it looks like this at least captures everything we need. So if I click generate from here, what's going to happen now is anything within that sphere is going to have a 0.25 millimeter element size. Everything outside of it is going to default to the 0.5. And it's chugging along. And there we go. So if I just take a look at the mesh, you can see here, pretty coarse over here, but much more detailed in the center. And this is about 678,793 elements, which is fairly good in my opinion. And we take a look at the element quality. The very outer surface looks bad in terms of skewedness, so we could improve that. The internals look a bit finer. So naturally, because it's just a demo, let's just say go with it. And because I want this to run a bit faster, let's make it a little bit easier on us. So I'll change the full size to 1 and the body sizing to 0.5, just so we can run this within a day, or at least within this one session. So this should finish fairly quickly. Better. So now we've reduced it to 100,000. So let's say this is your mesh and this is what you want. You can go ahead and exit out of this. Make sure you right-click this mesh feature and click Update. And right now, Ansys is telling us it's updating the mesh. And this is all ready because we have this little check mark here. Now we can go up to setup and actually do our boundary conditions, select our fluid, model, and everything. So right click edit. I usually click double precision on. You can pick how many solver processors you want. So let's say you had a 4-core setup on your computer, then you can type in 4 here. If you have any GPUs on your computer, like a Nvidia RTX or a AMD Radeon or something, then you can put 1 here or 2 or however many you have. I have 1, so I'll put 1 here. And then you can start. So click OK there. And this is what default Ansys looks like. So the first thing I would suggest you do is you do a mesh check. So go over here to check, click done. And this is the little console window. If you don't see an error here, you're in pretty good hands. Do a report quality. And we see your maximum element ratio here. If this doesn't throw off any errors, then you're also fine. Now, what I would suggest you do is also evaluate mesh quality. No issue. And right now what we have is a tetrahedral mesh. So if I click display edges, you can see we have our tetrahedral mesh. But what Ansys has is the ability to make what's called a polyhedral mesh, which has the same computational accuracy as the tetrahedral, but it has less elements to get there. So it is actually faster computationally with no loss of performance. So I suggest you just convert it to a polyhedral by just clicking that. And it's done. So now if you click display again, you can see here now we have a polyhedral mesh. And if you're curious, before we had, what was it, 100,000 elements or something? This reduced it down to 50,000. So essentially, it cut down the amount of nodes it has to process by half, which is useful. So now, in the way you work yourself through this tree is basically from top to bottom. So the first thing is, what type of solver do you want to use? Do you want to use pressure, or do you want to use density-based? In general, I say use pressure because if you're dealing with something that's moving at low speed and it's an incompressible fluid, which blood is, then you go pressure-based. If you're dealing with something that's very high speed and it's compressible, so like airplanes or missiles or something, just something moving at high speed that's compressing the air or the fluid as it's going through it, then you would go for density-based. You can also do a steady state or a transient simulation. For our purposes, we're doing a steady state. And you can also add gravity here. Now, what I'm going to assume is that gravity is going in the z direction. So if you see here our little axis here, z is along this dimension. So I'm going to say, okay, this is negative 9.81 in the z. So now that we have that set, let's go ahead and do the next thing, which is select our model. By default, it's SSTK omega, which works well for a lot of fluid situations, but you can also just click laminar instead. Truthfully speaking, unless you want to capture turbulence in your model, you can just click laminar. Otherwise, you can go with the default SST K omega. But let's say you're going with laminar. To just make things simpler, go with laminar. Now, this is where we select our fluid materials. By default, the solid is also included, but that's not a part of our simulation, so we're going to ignore it. And by default, the Ansys assumes the fluid is air. So if we double click this, we can edit this and say, no, this is not air, this is blood. And we can say, okay, the density of this fluid is 1060, and the viscosity is something we can pick. So if you wanted, you can go with like a non-Newtonian relationship. You can do a Corot model if you have constants available for that. But for us, let's just say we're going to go with a constant value, so it's Newtonian. And we're going to say this is 0.0033, so 3.3 centipoise. Change create, yes, and now we have blood. And in the subzone conditions, this is where you can select what type of fluid you want to use from our materials. So we can say, okay, the material name you want to use is blood, And if you wanted to, you can also say, oh, is my mesh going to be rotating, moving? Is any region porous? Blah, blah, blah. But for now, we're just going to say the only thing is the material is blood, and that's it. Apply, close. And now let's apply our boundary conditions. We have our inlet over here. We have 2 outlets and the wall. By default, the wall is assumed to be a no slip. So we're just going to accept that. But the outlet, let's change the outlet to, instead of being 0 pressure, we're going to switch this to being the average of human pressure is in the arteries and veins, which is about 100 millimeters mercury, which correspondingly is about 13,332 pascals. So we're going to change this to 133,332. Click apply, close. And for our inlet, we're going to pick an average velocity for flow through valves. So we're going to pick 0.315, which is not the highest it could possibly go, but it's not the lowest either. It's pretty much a middle of the road, what it could be for a large artery. So we'll go with that. And I think that does it for this. Methods. We can leave it a coupled. Don't need to touch any of this. Don't need to touch that. Don't touch that. Monitors. So one of the things that happens is Ansys Fluent tries to solve these Navier-Stokes equations using its model, and you can't just solve it perfectly. It's always a numerical approximation. So you have to tell Ansys, okay, I want to solve it to this level of convergence. So what you can do is you can click residuals here, and by default, Ansys tries to solve it to 1e-3 convergence for the continuity and XYZ velocity equations. But I usually set this to, when I'm least testing stuff, 1e-6 for all the equations. If I was doing this for a paper, then I would go all the way down to 1e-9. So click OK. And now we do initialization. Now for initialization, you can pick either hybrid or standard. If you click standard, then what you have to do is you have to select what you want to compute this initialization from, and you have to know some information about the geometry in question. But I usually select go with hybrid initialization, and by initialization, what I mean is when your solution is first starting off, what is the velocity and pressures everywhere in your model to start things off with? Because if you don't know where your solution is starting off, how do you go to the next time step, and so on and so forth. So what hybrid does is it takes a look at all your boundary conditions. It takes a look at the dimensions of your model. It takes a look at what the viscosity is of your fluid and everything. And it tries to solve what are called the Euler equations, which is a very simplified fluid model, and say, okay, I'm going to use these Euler equations as the initial condition for your system. And I want to say maybe like 95% of the time, that'll start you off on the right track. There are very few specific cases where hybrid initialization doesn't work. And in those cases, standard works better. So if we click initialize here, we can see here, it did 10 iterations and it arrived at a convergence of 8 times 10 to the -7. So this is good. If it didn't reach 10 to the -7, what you could have done is click more settings and increase the number of iterations to reach convergence. But we did, so nothing to do there. Now what we can do is, if we go over to runner calculations, I would suggest you do a check of your mesh. And it says, oh, just in case, do a check of your mesh, see if everything's good. So do a check. So we didn't get any major errors here, just some info. And we now, if we do a check case, no recommendations to make. And we select how many iterations we want. And by default, I'll usually say just pick a really big value, because the idea is as long as your solution is continuing, it's going to eventually reach convergence. For us, it would be those 1e-6 values. And once it reaches those values, the solution is going to end and we're going to get our results. But if we select too few iterations to do, it might never get to 1e-6. So I just pick a really big value, like 2000. And we're probably going to reach convergence way before this anyways. So I think that's it. If we were doing a transient analysis, we could have also done some time statistics, and we could have done some auto saving of quantities per time step. But because this is steady state, well, whatever final solution we get is the final solution we get, because it's steady state, just a single time point essentially. So now I think we're ready to actually run our model. Give it a quick save as well. So Control S. All right, give it another save. So while this is going on, any questions?
Yeah. Has there ever been any case where even 2,000 iterations is not enough?
If your geometry is inherently not suited for a steady state solution, then you might never reach convergence even after 2,000 iterations. What I mean is if you have some weird discrepancies in your model that cause the fluid to not want to reach a stable solution and inherently want to like flow one way, flow the other way or something, then your model might implicitly be better off being a transient case and impossible to solve for steady.
Gotcha.
Because the idea is for there to be a steady state solution, you wouldn't see a transient difference in your final solution if you looked at it now versus if you looked at it 10 minutes from now. But if your geometry is such that it has a bunch of issues in it that cause the fluid to flow one way, but then because it's flowing this one way, it causes a weird whirlpool pattern there that causes the fluid to go this way, and then that causes a turbulence issue over here. All that is very temporal effects, which does not lead to having a steady state solution.
Right. Yeah. So a lot of eddies and what's it called, low pressure disturbances.
Yeah, eddies, low pressure zones. Often, if you have any small crevices, that can also lead to it. I know in my lab, at least, we have these bioreactors we make for our cell conditioning, and that geometry is not friendly for a steady state solution. It'll always start oscillating because we get these little vortices that start shedding on some areas. So for that, you always have to go with transient. You can't go steady.
Okay, thank you.
Yeah. All right, and it's saved. So now we can go ahead and click calculate. And if we do that, we're going to get a little graph here that's going to show us the iterations and the continuity XYZ velocities, what their final values are per iterations. And the idea is as the iterations go on, these values should start dropping, and eventually reach our criteria that we set. And when it reaches the criteria that we set, then we find our solution and it'll exit. I bet you anything Zoom is taking up some resources that Ansys wants to use.
Yeah, same thing happens here. Whenever I try to use Fusion 360, I got to close down Chrome and only open up Zoom and Fusion. Otherwise, it's very laggy.
Of course, that's what happens. So maybe I'll give this perhaps a minute. If it doesn't really start up, I'll just exit this. And thankfully, I already had the solution calculated beforehand. But we'll see if this wants to start up.
So more or less, when calculating solutions, what would be the expected timeline for it to solve? Like how complex can it be?
Oh, you can get really complex. I've had solutions that, or I've had simulations that go longer than a day, or even days before. And that was when I was running really large models that were 1 million plus elements with nothing else running on my computer. But I've also had the exact opposite where I've had very simplified cases that run in less than a couple seconds. Like it'll take longer to set up the model than it is to solve it.
Right.
Yeah. So it really depends on what your model is, what the details are, your boundary condition is steady state, transient, so on and so forth. All right. I'm going to give up on this. Interrupt that. So I closed all that down. So let me go back here. Open up Ansys again. So what you would normally see is this graph right here where our solution starts and then it drops, dropping until we reach convergence. And once it does, it exits and you get your answer. Now, what I would normally do is you would look at the waterfall flux reports and see if based off your inlet and your outlets, the idea is mass should have been conserved. So if you take all the flow that's going in from your inlet and all the flow that's leaving from your outlets, they should exit out to 0, or they should sum up to 0, and that's what I get. I get a net result of -4 times 10 to the -8, so 0. And you should also check if your inlet boundary condition was preserved. So if I do what's called a surface integral report, which is something you do in Ansys, and area weighted average of the velocity and magnitude on our inlet, you should get the same result as your inlet boundary condition, which is what I got, 0.315. So at least numerically, things seem to be working right. So here's our simulation again. I'm going to go ahead and delete this. And then usually what happens is now you have your solution and you want to go to your results. So if I make a separate results thing, where is it? Fluid results. Grab this, transfer that there. This will open up what's called CFD post, which is a special little environment that lets you process all your CFD results. So if we click wall here, here's our actual geometry. And the first thing I would say we would be interested in is, let's say we want to know about any areas of high pressure on our model. Well, if we click this wall here, we can click render or color. And instead of coloring by constant, we can say color by variable and say color by pressure. And then make this color by a fluent rainbow, apply. And if you notice, we have this pressure concentration of about 251 pascals right at this bifurcation point. So that's where the flow is diverging. So that'd be one thing people you might be interested in. Another thing you can take a look at is, for example, do a volume rendering. And let's say you want to see what the volume is around your surface or around your geometry. So you can say, okay, I want to take a look at the volume or the velocity. And you can see here, we get a volume rendering of the velocities in centimeters per second. So it's like going up to like 63 centimeters per second, minimum is 0. And if you notice here, in our bulge region here, we're getting areas of very low flow, almost 0. So that's indicating we have stagnation regions in this. So this will be areas where we might get clot formation occurring. So this is all interesting stuff that you might be interested in. Now, another thing that you might want is to do like a planar cut through this surface. So like a cut that's going right through here, let's say. So to do that, you can do insert a plane. And then we do cut like that. Pick one point there. Pick maybe this point right here. And maybe that point. Let's try to see what type of slice it makes. Nope. So you can see here, if I turn off this volume rendering, it made a plane that cut right through it. And what you can do now is, if I turn off the wireframe, scroll out, we can actually use this plane cut and color it based off of something we want. So let's say we want to color it based off velocity. Then what we can do is click this contour and say our location is going to be plane 1 and color it based off velocity. And let's say give it 100 contour lines and plot. And there is a better representation of this stagnation region I was talking about. If we turn off lighting and culling and showing contour lines, we get that. And we can actually bump this up to maybe 250. So you can see a better representation for it. And if we want to also add in, let's say, the direction the fluid was moving, we can do these vector plots. So we can say the location is plane 1, and the variable is going to use for direction is velocity. And the color, we can say do a constant color, black. And if you notice here, large values here, and then the flow sort of diverges here, and we get these little circular regions right here where the flow is just oscillating around. So that might be something you're interested in looking at. And one other thing that usually people are interested in is the wall shear stress on these arteries. So what you can do is actually do a contour of the wall shear, and the location would be the wall instead. And let's give this also 100 points. And then you can see here that we have areas of very low wall shear stress right in this region here. And if you want to know what the specific value of the wall shear stress was around this region, you can click this probe icon here. And if you click here, like let's say right there, you'll say, okay, the probe is located at this XYZ coordinate, and the value for the wall shear at this location is 0.2 pascals. So 0.2 pascals is correspondingly 2 dynes per centimeter squared. So you just take whatever Pascal is and multiply it by 10. And in a lot of physiology journals, they're reported as dynes per centimeter squared. And generally, you'll start getting thrombosis occurring if you're anywhere from like 1 to, I want to think off the top of my head, 5 dynes per centimeter squared. So if you're in this higher moving region here, you would have 54 dynes per centimeter squared. So you wouldn't. So the blood here would be moving too fast for coagulation, but the blood in this pocket region here is moving too slow, and you would start developing blood clots and platelet aggregation here, and that could eventually embolize and go downstream, cause heart attack, stroke, who knows. But this would be the perfect chance for you to also start doing experimentations such as, let me change the rendering. Where is it? Labels. So this would be a perfect chance where you could actually, for example, do like a stent geometry, and you can put it inside of this artery, and then see if that improves the flow or not. Or you could maybe figure out a way of expanding or contracting this region here through some surgical technique to restore the flow from the inlet to the outlet. But these are all surgical techniques and computational stuff that you can look into now that you know what areas might need to be moved or adjusted. And with that, I think I'm done. One other thing I wanted to show you guys was Ansys has this new thing called Ansys Discovery Live. It came out a couple years ago or so, but they've improved it a lot. And basically, it's a way you can rapidly check through different design concepts that you have and do simulations on them without having to go through the hassle of meshing and solving each time. And it does this by leveraging your GPU. So for example, you have this heat sink and you have the airflow going around it, but you can very quickly start editing the geometry and then seeing the results. In this case, we have a static structural analysis. And what you can do is, and this could be a fluid. And what you can do is you can change, for example, the positioning of this geometry and see how that affects your flow instantaneously. You can see how different patterns or different sizes of this heatsink start affecting the heat transport in real time. And yeah, this is just this other thing that Ansys has, which you have access to. So it's just called Discovery, Ansys Discovery 2021 R1. But the lab computers also have this. So yeah, you can gain access to that as well. Any questions?
Yeah, for Discovery Live, is there any setbacks per se for using it? Since I know I think it might require some HPC computing, since you do it live.
Not HPC. You just need to have a good enough graphics card. So if your graphics card is NVIDIA anything, and it can play for the most part any game that you're working with or you usually play with, so any high quality game, then it can run Ansys Discovery Live pretty simply. So as a reference, the one I have is NVIDIA GeForce GTX 1070, and it can run it perfectly. But Ansys does have a list of recommended GPUs that you should use. So if you want, you can just Google that. Otherwise, most off-the-shelf GPUs that are used in most gaming computers or decent enough workstations will work fine with this.
Is that normally a premium product, or is it accessible to FIU students as well?
It's accessible to FIU students. So if you access the lab computers through the VPN option I talked about yesterday,
Yep.
it should be available because it is part of the Ansys Discovery suite. However, if you want to run it on your laptop locally, then you can just do Ansys Discovery Live Student. So under the free student license, you can click Ansys Discovery Student and then download this, and that will basically be your Ansys Discovery Live Student Edition. Naturally, there are restrictions. So yeah, so no geometry export, academic restrictions, fluid can only be 500,000 cells per node, structural can only be 128,000. And these are your limitations, but if you wanted to, you could just use this to quickly see visually what the results are, and then you can go back to your CAD, either in SolidWorks or whatever, and then adjust it there instead of going through here.
Awesome, thank you. One more question. For the actual CAD model, is it assumed to be a specific material? In this case, the wall, or the model for the physical geometry.
The CAD model is literally just points in space connected by triangles. You apply whatever material you want to it. So Ansys Discovery Live has a built-in material library, but you can also just say, oh, this piece right here in my component is actually made out of steel. This one's made out of rubber. This one's made out of wood. I don't know, whatever. And if you're dealing with the fluid component, you'll say, oh, this is, Ansys has a list of, oh, air, water, oil, or you can make your own fluid that has certain properties.
Gotcha. And so in this example, the material would be from the library of lists, from the list of libraries.
Yeah, although in my experience, Ansys doesn't really have like biological materials too well. So you'd probably have to like know what the fluid properties of blood are beforehand, or if you're doing like cardiac tissue or something, you would have to import that cardiac tissue as your own custom model, which you can certainly do if you have like engineering data and you open this up. Usually cardiac tissue has, where is it? Usually cardiac tissue is a hyperelastic type of tissue. So you can try like approximating it with Neo-Hookean, Ogden, Muni-Rivlin, these type of models, in which case you would have to provide parameters, so like heart. And let's say we have like a 5-parameter Muni-Rivlin. You would have to provide these C10, C01, C20 incompressible parameter constants. And usually you can get these from literature.
Okay, sounds good. Thank you.
No problem.
Well, unless you guys have any questions, I want to once again thank Asad for showing us the steps towards being able to use Ansys Fluent, and specifically for this aneurism model. Very insightful. If you would like to continue the discussion, feel free to contact Asad. Pretty sure he'll be happy to help you. But yeah, I wish you guys very well, and hope you enjoy your weekend and have a great day.